Greetings, everybody. This is example 2. This is the second video for the Chapter 7 lecture notes, part 5. It deals with COE and friction, meaning how to apply conservation of energy when there's friction. And here in example 2, you have two blocks, M1 and M2. They're connected, with a string via a frictionless pulley. M1 lies on a surface where there is friction. There's friction between M1 and the table. And then the system is released from rest when the spring is in the equilibrium position. The spring has some spring constant K, M1 here, and what happens, it's released when the spring is at equilibrium. Then what happens is, let me just backtrack slightly. So the system, meaning M1 and M2, that's our system. It's released from rest, meaning initially M1 and M2 are at rest. Okay, so KE initial is 0. And furthermore, it's released from rest when the spring is at equilibrium. All right, so we know KEI is equal to 0, and we know that the initial potential energy of the spring is 0. Then what happens is the falling mass, M2, falls through a height of h before coming to a stop, which means that if M2 falls a distance h before coming to a stop, M1 will move horizontally a distance of h before coming to a stop, because they're connected. So if M2 falls a distance of h, M1, i.e. the spring, has to be stretched a distance of h. In other words, when each mass is in the shaded configuration. Okay? And I wanted an algebraic expression for the coefficient of kinetic friction between M1 and the surface. And I wanted it in terms of M1, M2, H, K, and obviously G. Okay, now remember, M2, it might not be readily apparent, but M2 is clearly not touching the side of the table. So there's no friction involved with M2. There's clearly friction between M1 and the tabletop. System is released from rest, and then when M2 has fallen a distance of h, and M1 has stretched the spring a distance of h, after that occurs, they're both at rest again. You see, because coming to rest. So KE initial and KE final are both 0. Okay? Now let me choose the initial position of M2 as the reference point, meaning that's where the gravitational potential energy is 0. Now in this case, Fk is mu k Fn, which is mu k M1g. Remember, friction is only acting on M1. Okay? So again, just to recap, if M2 falls a distance of h, M1 moves a distance of h, which means that the spring is stretched a distance of h. Makes sense, just look at the figure. Okay? We know Fk is mu k M1g, reference point chosen as shown with the blue dotted line. Okay, apply conservation of energy. And again, I'm writing the whole equation, KEI plus PEI minus EFR equals KEF plus PEF. Well, we know KEI and KEF are 0. So just, they're gone. Ignore them. Well, what is PEI? Well, PEI is 0 because initially M2 is at the reference point, meaning it has no potential energy. Now, I don't care about the potential energy of M1 because it never changes. The height of M1 never changes. So I don't have to worry about the potential energy because it never changes. So I don't care about the PE of M1. I just want the PE of M2. So the initial potential energy is 0 because initially M2 is at the reference point. Okay? So what's KEI? 0. What's PEI? 0. Then I have minus. EFR. Well, what is EFR? Well, it's Fk times h. It's kinetic friction force times distance. It's Fk times h. Remember, m1 moves through a distance of h. Because if m2 falls a distance of h, m1 has to move to the right a distance of h, meaning the spring has to be stretched a distance of h. So again, left-hand side, KEI is 0, PEI is 0, minus, EFR is FKH. Now, what is the final kinetic energy? 0. We already know that. Release from rest comes to rest. So KEI and KEF are 0. Well, what's the final potential energy? Well, the final potential energy is the spring potential energy, 1/2 kh squared, because the spring is being stretched a distance of h. Now, what's the final potential energy? What's the final gravitational potential energy? Well, it's due to m2. m2 is now a distance of h below the reference point. That dotted line, the blue dotted line, is the reference point. So the final gravitational potential energy is negative, and it's m2gh, because m2 is a distance of h below, meaning that PE is negative, distance of h below the reference point. Now see, that's why we prefer the energy method. I didn't have to draw the tensions in the string. All I have to know is that the normal force on m1 is m1g. You know, if you want, you can draw Fn in the positive y, m1g in the negative y. Those are the only two forces acting on m1 in the y direction. Obviously, because it's not accelerating in the y direction, Fn must equal m1g. That should be second nature by now. So anyway, so we have, by applying the conservation of energy equation, and this is important, you want to understand how that equation then gives me this. You can understand that then, and now it just becomes a straightforward algebra problem. I want an expression from UK. So I have to take this equation and solve from UK, where all I did is, what is Fk? Fk is mu k m1g. And I still have the negative and the h. The negative and the h. Solve that for mu k, and you get mu k is equal to m2g minus 1/2 kh all over m1g. Very basic algebra, but you want to understand these three steps right there. And again, KE initial and KE final, they're both 0. Again, release from rest comes to rest, so they're both 0. Now, the initial potential energy is 0 because when the system is released, the spring is at the equilibrium position, so there's no spring potential energy. Well, when M2, I'm choosing the initial position of M2, indicated by the blue dotted line. That's my reference point, meaning initially the potential energy of M2 is 0. I don't care about the potential energy of M1 because the gravitational potential energy of M1, because it doesn't change. Okay, so again, KE initial 0, PE initial, both spring and gravitational, 0. So I have minus EFR equals, and I know KE final 0, so I have minus EFR equals PEF. Well, minus EFR, well, what is EFR? FKH. Yeah, minus. What is the final potential energy? Well, the spring is now stretched a distance of h, so that's 1/2 kh squared. M2 is now a distance of h below the reference point, minus M2gh. Solve this equation for mu k. And let me go ahead and get this posted.